So let's go through the proof of the main theorem in 1.4. This is on page 37 of the text. So the theorem says, suppose you have a matrix A, m by n matrix, then the following statements are equivalent. So the first one is that for every vector b in Rm, the equation ax equals b has a solution. Next, every b in Rm can be expressed as a linear combination of the columns of A. Third, the columns of A generate all of Rm. And fourth, A has a pivot position in every row. So notice, this theorem is not saying that these statements are true. The theorem is saying that the statements are logically equivalent. So they're either all true or either all false. So one reason such results are so useful is that they relate statements that are difficult to check, so in this example it would be items 1, 2, and 3, to something easy to check, like item 4. Right? So notice that to check whether or not A has a pivot position in every row is just a Gaussian elimination and then look at the pivots kind of question. As soon as you can reduce a problem in linear algebra to row reduction, then you win. Note, instead of showing the equivalence of each of these four statements, which would involve showing 1 if and only if 2, if and only if 3, if and only if 4, it's enough to show 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. So recall that if I want to show a conditional, a P implies Q type of statement, or an if P then Q statement, I want to assume that P is true and then try to deduce Q. So let's go through the proof. Let's start with 1 implies 2. We start by assuming that Ax equals B has a solution for each B in Rm. And we want to show that every B in Rm can be expressed as a linear combination of the columns of A. So let's fix a vector B in Rm. Right? So whenever you're trying to do one of these, show every something something satisfies some property, what you want to do is fix a generic element and then try to prove the statement for the generic element. So we want to show every vector B in Rm is a combination of the columns of A, and so we fix a particular B in Rm. Now, we're going to express the columns of A as A1, A2, all the way up to AN. And so by assumption, Ax equals B has a solution. So there exists an n-tuple, S1 up to Sn, such that A times the vector S1 up to Sn is equal to the vector B. By definition of matrix vector product, that tells us that S1 times A1 plus S2 times A2 all the way up to Sn times An is equal to the vector B, which expresses B as a linear combination of the columns of A. So now let's turn to 2 implies 3. So we start off by assuming that every vector B is a linear combination of the columns of A. And then we want to show that the columns of A generate Rm. So again, we're going to write the columns of A as A1, A2 up to AN, and we want to show that the span of A1, A2 up to AN is equal to Rm. So just recall, if I want to show two sets are equal, so two sets S and T, that's two parts to it. And we need to show that S is a subset of T and T is a subset of S. Okay, and so that's what we're going to do. Since the columns of A are in Rm, it's clear that the span is a subset of Rn. And that's because the span is just the set of linear combinations of the columns A1 up to AN. Right? So in particular, when you take linear combinations, you can't ever leave the Rm. Right? You're just taking linear combinations of vectors in Rm. Okay? So now that shows containment one way, and now we want to show containment the other way. So let's take a vector B in Rm. right? And then we want to show that it actually lives in this span. Well, by assumption, B is a linear combination of the columns of of columns of A, and so that tells us B lives in the span of A1 up to AN. And that proves that Rm is a subset of the span. And so that ticks off both things we had to check, and therefore the span of the columns of A is equal to Rm as desired. Now let's try to prove 3 implies 4. So note that a conditional is logically equivalent to its contrapositive. And so what does that mean? That means if I want to show P implies Q, that's logically equivalent to showing, or to the statement that not Q implies not P. And so in this case, proving not 4 implies not 3 is easier, and so that's what we'll do. So we start off by assuming not 4, namely that A does not have a pivot position in every row. And we want to show that there is a vector B in Rm such that B is not in the span of A1 up to AN, right? Not in the span of the columns. So we'll let U be the reduced echelon form of A. And since A does not have a pivot in every row, that tells us the bottom row of U is all zeros. So then the augmented matrix, U, and then the vector 0, 0, 0, 0, 1, corresponds to an inconsistent linear system. If we undo the row reduction from A to U, we get, if we undo the row reduction from A to U, and we do that to the augmented matrix, U with 0, 0, 0, 0, 1, we would undo it and get A and then some vector B in Rm. And that tells us Ax equals B is inconsistent, and so B is not a linear combination of the columns of A. And finally, we need to show 4 implies 1. So we start off by assuming that A has a pivot position in every row, and we want to show that for every B in Rm, Ax equals B has a solution. So this is very similar to what we just did. We're going to let U denote the reduced echelon form of A. The augmented matrix AB row reduces to UD for some vector D in Rm. And since U has a pivot in every row, the rightmost column of AB, the augmented matrix, can't be a pivot column, right? Because all the pivots were used up in the rows. Thus, Ax equals B then has a solution. And therefore, 1 implies 2, and 2 implies 3, and 3 implies 4, and 4 implies 1, and so 1 through 4 are logically equivalent.